So we are in the first part of the microwave engineering. Before our midterm, the test range include only chapter 1 in your textbook. So if you have any question, if you don't understand, I'm talking about, maybe you can read our textbook, David Poza. Okay, only chapter 1. We have, I think we may contain enough material to have the first exam for our midterm. Okay, it should be supposed to have enough material because I need to review your something like Maxwell equations or some common sense about the vectors, scalar, something else. I need to give you more extra knowledge from other books. Okay. So even the main story cover only the first chapter, but I will give you some extra knowledge, background knowledge to help you to understand chapter 1. Okay, that's what I'm trying to do in here. Then come back. So for the chapter 1, the title of this chapter is Electromagnetic Theory, E field and H field. If you have this textbook, you can check. The title is EM theory. For chapter 1, I cut that in half. So for this PowerPoint is only part 1, just only half of the chapter 1. Okay? So this part of the chapter 1 covered our review knowledge about Maxwell equations we did last week already. I introduced you these 4 principles, these 4 important equations. Those happened again and again in our common life. Those are very important. But honestly, I'm a little bit surprised. Like some of you maybe you don't precisely understand which one is which. So maybe now it is a chance for you to know which equation is which. Okay, like what is Gauss's equations, what is Ampere's law, what is Faraday's law. Those are, like a common sense for electronic engineering or electrical engineering, or probably students or engineers. Okay, so it's time for you to understand these 4 equations. After you have the background of Maxwell equations, we also have some applications. The end of last week, I tried to explain boundary condition, just only part of the boundary conditions. This is the first thing in our class to apply Maxwell's equations. Okay, the reason I introduced boundary condition because this is what the book said. In the book, they explained, David Poza explained Maxwell equations, and those are 4 important equations, 4 important relationships, then boundary condition. Okay? Okay, for more details, you can refer to your textbook about boundary condition. Then I will keep going, but before I start, I'm trying to tell you more about what we are going to learn before your midterm. Okay? After boundary condition, I will try to explain what are waves looks like. I tell you that there are 4 equations about when people tell you about the electric field, magnetic field, right? I give you this notation. This is a vector. This is a vector, maybe vector function. It's an unknown vector, right? I just tell you it's E, it's H. Then you are supposed, it is very common that, it's very natural that you will ask me, what is E? What is E? You tell me that's an electric field. You need to use a vector to present your electric field and the H field, right? Like what I asked you, the question I asked you last week is, give me an example about vector. Yeah, I asked you scalar because scalar is the thing you are very familiar. You don't need to learn. When you are familiar, you don't need to learn. But the thing you learn here is vector. I ask you, and some of you maybe give me the equation like, okay, in the rectangular coordinate, you have, maybe you use, I forgot the number, but maybe 2z plus 3x. Okay, this is an example, right? Okay, this is an example. Can I say that for a E field, can I? How? What kind of the structure? What does our E field look like? Or what does our H field look like? What does it look like? Can I write down anything? Can I? Of course not. E and the H, they have their own function. Like I have different magnitude or amplitude, right? I have phase. But how? How do we know? This is the third part we may explain after boundary condition, okay? What is E and what is H? What does it look like? Of course, we will need to simplify the conditions to have a very concrete and a very basic form to describe the E and the H. This is what we are going to do today after we introduce boundary conditions, okay? Then the story will go on. After you know what does E and the H look like, then you can see what happens if there is an E field or H field when this field is in the lossless material, in some material. Okay? This is the part one. Okay, and I will give you some hint about the second part. What will we introduce about second part? After you already totally understand about E field and H field in lossless medium, after you know that, this is a very simple, the simplest case. Then I will put your E and H field in some special materials. Not lossless, I have lossy materials. I will put your E and H field inside the, not only lossy, maybe I will put them in the metal. What happened to a metal? What happened to some special material? Okay. Then after you learn that, your E and H field will start to move. And this field will collapse to, you bump to some boundary. After you learn your field is inside different materials, right? Then your field will start to travel. After it traveled, your touch will bump into another material and something will happen. Those are one of the most important parts for the end of the part one. Okay? Okay. So now you prepare mentally. Now you mentally prepared what we are going to do, right? Try to explain Maxwell equation, those relationship. There's an application. After you know application, we try to explain what does the E and the H looks like. And I put that in the lossless material, put in the lossy material, put in the metal. Then I try to make it move.
Like waveguide?
Not yet. There's still nothing.
Okay.
There's still series. You still don't see anything. I just move the field. The field can bump into something. Then you will have a reflected insertion waves. There are many different. Yeah, those are the most important topic in chapter 1, and we will have a midterm and we will see how much you understand. Even you have the open textbook test, how much you can feedback to me. Okay? Do anyone have a question or you don't understand? Is that too fast or? Okay?
Don't worry about that.
Don't worry, because we will take a video, right? You can slow down my voice. Okay, this is a review. So we introduced Maxwell equations. I told you that you need to write down, but there are more details I introduced last week. So what are those? I spent a lot of time to explain all the notations, what they are, and what kind of condition they are, and different forms. You can find the answer from my slide, so I don't worry about that. Yeah. And what is Gauss's law? And another equations, another derivations, and Faraday's law. Now, one of the good things that I use a computer is I will have the animation. It can move. And if I use the iPad, this cannot move. If you change your magnetic field, you insert your magneto in a wire, in an inductor, maybe you will introduce some E field and you will determine, you will generate current. Okay, that is Faraday's law. And Ampere's law, if you have a current pass through a conductor wire, you will introduce, you will create an H field, or you say B. Then those are Maxwell equations, another, more Maxwell equations. Okay. The boundary condition, after you understand those 4 equations, and we try to apply the equations inside the boundary condition. Okay. You can simplify the question by, you just use a line. You don't use this is a curve boundary, right? You can use a straight line, maybe it's easier for you to understand. But in the textbook, we try to explain this question in a more general form. So why we will have this? Because this equation is supposed to be allowed to apply to any boundaries. So, okay. One more student does anyone want to have extra extra point to help us to review what are the meaning of those notations? Anyone? Okay. Just try to, yeah.
The electric fields are perpendicular to the surface.
I mean each one, and do you want to explain that to help other students to remind what we learned last week? Why? So what are those, and what is the condition of this picture?
Also, try this.
This is a picture to discuss about the boundary conditions. Yeah, keep going.
When the EM waves they go from one medium to other medium, the electric flux density and magnetic flux density they changes. So that's,
yes,
and it's
yes. And how about those? What are those notations in the? What is this condition? And what are those notations? Or you think you already covered everything you are trying to say?
D is the electric flux density.
Which one? D? Okay, so why do we have Dn2 and Dn1? Why?
The two mediums.
Yes, there are two mediums because this is a boundary. Like we have a medium 2 and a medium 1. So they have different D. And as you said, D is
electric flux density.
Yes, electric flux density, the lines, those lines, right? Flux. And why do we write down N1 and N2?
Because on a surface there are so many electric field lines.
Yes.
So that's one of them. So
okay, what does N stands for? What does N stand for? 1 and 2 means for medium 1 and medium 2, right? Why do we write down not only D1 and D2? We write down also N1, Dn2. Why?
Like 1, 2, 3, 4, 5.
Don't know?
Like 1, 2, 3, 4, 5.
N? This N. Okay. I will try to remind you that. How about these two? Can you explain these two again? Now I want to ask Abi because he was here. Maybe you can try next, okay? Yeah. Abi.
It's the electric field.
Yes.
In two mediums.
Yes. And what does T stand for? Why we write down T? Why we write down N?
N is 1, 2, 3, 4, 5.
Number 1, 2, 3, 4, 5.
Like numbers.
Yeah. How about T? Is that T2, 3, 4, 5? Why we write down T here? Your answer is very close, but you need to be more concrete. Okay, maybe you want to finish what are the different we use N or T. Close. Okay, maybe I give him more opportunity. Okay. Yes. Yes. Very good. Okay. I give you a new rule about.
Okay. Only people get my card can get extra point. Okay. I will keep the card
to Zhang Zhenjia and Abi. Okay. You are close enough, but you need to make it more complete. Okay. Then you can change your extra points after that. The cards help me to remember which one is Who got an extra time? Okay. You guys want to take a little bit rest and you can continue your quiz. Okay? In the static state, which means the time is stopped. So far, we are trying to talk about in a more general. Maybe I should not say time is stopped. I should say we are talking about a more general situation. Okay, so E field, D and the D and the J and the M and the H, all of them are in general. I didn't say they are moving. I didn't say they stop. It's not stopped yet. It's just for all the conditions. Okay? When you have two materials, this will happen for all the conditions. This is a very general condition. Okay? These boundary conditions will happen for all the situation. Okay, and this is one of the thing, is the first boundary condition we tried to explain last week. I use the Gauss's law in this is a differential form. Okay, if I look at this equation, I regard this equation like there is a boundary and I have a surface integration. I have a surface, how do I say that? I covered a cylindrical surface, and then this happened on the boundary. Okay, on this boundary. According to Gauss's law, which means if I integral our electric flux density for a closed surface, I integrate that, I will obtain the total charge inside this area. Okay, this is what Gauss's law tells us. And if we do the same thing on the boundary, if this is true, we want to obey the Gauss's law, and we assume the height of this cylindrical is as small as enough, then you will look at this question like we have only two surfaces, and these two surfaces has different direction. For the top one, it's going to up. For the bottom one, it's going to down. But we define the direction of electric flux density in the same direction, so we can obtain this result, right? It's going to up and down, because here on this picture, median 2 is in the bottom, in the top, right? Median 2 is in the top. And when I define this direction, D is the same as the direction of the top surface, you will obtain a positive result by N dot D2. This is a positive result. Okay, N dot D2 to the same direction. This is a positive result. For another portion, because your dN1 is in the same direction as dn2, right? But because I want a closed surface integration, so the surface direction of n here is going to this way, but in the bottom, n is always outside this area. So n will become the opposite direction of dn1. Therefore, you will obtain a negative product between n hat, this is a unit vector, dot d1. d2 hat dot n, it is dn2. Okay? You have only this direction left if you use, and this d2 means all the direction of d2. This is all the direction of d2, and dn2 means only the perpendicular direction of d2. Okay, any notations they have the meaning. Okay, n2 means this direction, d2 means any, all the d2 here. 2 means median 2, 1 means median 1. Okay, now you get it? Okay. Okay, if you have any question, or maybe I make a little bit mistake in the class, maybe we should refer to your textbook. That's why we should buy textbook. Everything, I think it's more accurate in the textbook, but in the class, maybe I will make some mistake. Okay, we can discuss. I will pretty appreciate that maybe you can help me to correct, to make my class more smoothly and more correct. Okay, just tell me if I make mistake. So this one is all the direction of D and the dot, the normal. So you got this one, and the result, why it will become the eta. This is a low, we call this low S. Why we have low S here? Can anyone tell me? Why is low S here? Why we have Q here, right? But now it become low S here. Can anyone tell me why we have low S here? You have the same thing, you dot everything here, and then you get low S. Anyone? Extra point? You want to try it? Why? Yeah, so what is low S? Give me the question, which is easier. Close.
It's a surface charge density on the surface.
Yes, so what is the equation? What is low S? Low S is, maybe that he almost done, so, but I want you learn to explain that completely. It's very important thing. You need to explain things completely. Maybe you think it's complete, but I want to be more accurate. My question is, what is low S? What is the equation of low S, and how do we obtain low S? What is the low S? The relationship between low S and the Q. What is? If we already know Q, right? Just give him a little. Maybe this is not a very hard question, but he didn't describe very accurate. What is low S? equation of rho s is q divided by I.
Area.
Yes. But you already got an extra point. It's okay. It's okay. So, what is rho s? The definition, the meaning of rho s is surface current density. Yeah, the area is correct. Right. So, the equation of rho s equals to, you can refer to this one, rho s equals to Q divided by delta S. Then I will ask you, what is delta S? Delta S is the area of the top and or for the top, but top or bottom side of these two. But because we have h equals to 0, right, goes very small to 0, your enclosed surface integration become only two surfaces, 2 delta S, okay? But this one, it will become this one and this one, but the direction is different. So, yeah, you put your delta, there will be a delta S. You will put your Q divided by delta S here. Then you obtain, it will be the rho S here. Okay. For another equation, the number 4 equation, you get the same result. But for the number 4 equation, because that equals to 0, so you obtain very similar thing, except that the left side is 0 here. Okay. So back to our reality. So what can we obtain? These two means if I have a field here, I have the field here, okay, my flux density to this direction, they are always the same as if there is no charge on the surface, D2, dN2, dN2 and the dN1, they are the same if there is no charge on the surface. But if there are some charge on the surface, you need to use this equation. Okay? So we got the first equation. But maybe you will always encounter only equals to 0. I will tell you, oh, there's no charge on the surface. So dN2 equals to dN1, and the bN2 equals to bN1. Understand? This is the first equation. Now, first two equations, they are first two equations. Okay. For these directions, they are the same if there is no charge on the surface. Okay? Okay, remember the boundary condition 1, boundary condition 2. We will use this later. Okay? Okay. Another two boundary conditions is more, I don't know, is that easier or more difficult? I'm not sure. You listen, okay? For this one, you try to use this equation, the number 3 and number 4, you use the closed integration of the surface. It looks like you need to think that in a 3D dimension. Okay, this is a 3D model. But if you want to use the boundary conditions from the first two equations, you use number 1 and number 2 equations, and then you use the 2D dimension to think about this equation. It is a 2D Okay? Because of these two equations, you apply this equation and change that back to the integral form. You obtain this one is, what is this equation? Anyone? No extra pi, but you are supposed to answer this equation. What is this equation? Can anyone tell me? No extra pi?
Amperes?
Ampere's law? Yes, Ampere's law, yes. If you, okay, how to remember? If you see J omega means partial differential to T, right? Which means time is changing, right? Time is changing. What is changing according to time? B. If your magnetic field is changed with the time, which means you move your magneto, you change the B. This is what happened in real world, right? And what will happen? The change of the magnetic field can introduce your induced E field, which can detect by your multimeter. You can detect the current here. This question. If you see that here, they will introduce this one. Okay, so let's correct. Abi, good job. But you already got a car, so yeah. Every week one car only, okay? But you can still answer, it's fine. Don't worry because nobody want to answer, it's okay. It's good. It's good to help you to understand. Yeah. So, Ampere's law, but it's longer because you write down something, maybe later this fixtures never happen, but you try to write down because it looks more beautiful. This is current density. This is electric current density. This is magnetic current density. Current, yes, but that never happen. You write down because it looks beautiful. Yeah, that's okay. We just follow our task book and write down. Again, then how to explain, how to apply the Faraday's law on the boundary surface. How? We do very similar thing, but now it's in 2D. Here, you see there is a linear closed integration. Not surface. Surface we use everywhere the surface. We integrate the surface. But linear is much easier. You try to put a loop. There's a circle or rectangular. There's a shape. But the most important thing is it is closed. It must be closed. Close. It's it's. I don't think I need to explain closed, right? Closed. 封闭的 closed. It's not, yeah, it's closed. Okay. So you put a circle which is closed. Similar to what we did before, we assume that this is also the edge of these two sides. The length of the edge of these two sides, we assume that it's as small as possible, it's close to 0. So what will happen here? We have only two lines here. But because it is a loop, so the direction of integration of these two lines is in the opposite way. Because it is a loop, right? So for the top side, it's going to that way. And for the bottom side, it's going to right way, they are going to different way. Very similar thing happen here that if you define the E field here, the direction of E field in the media 2 is in this direction, and you also define the ET1 in the same direction, they need to subtract to each other because of the direction of this and this line, they are in a different direction. Okay, so we apply this equation, we integral the E field according to a loop, a closed loop, then you obtain the result will become this one, right? Will become this one. The hardest way to explain is the direction, and I might ask you this question in the midterm test. The question is more difficult to answer the question. If regardless the direction, we look at the magnitude only first, okay? The answer is very similar. ET minus ET2 minus ET1 will equals to your M divided by your delta L, right? If you think only the magnitude, you don't think about the direction, it's easy, it's okay. The difficult part is what is the direction of your MS and what is the direction of E. I try to explain that, but I can see the website. I try to write it down because it's a little bit difficult. About the direction of the boundary condition too, okay. I try to explain this, the same, can you do that? It's clear now, okay. I try to explain that, but I need to simplify the question. I put the X, Y, Z, the direction of X, Y, Z here to explain this question. But in the textbook, it is a more general way, okay? But to explain that, to help you to understand, if this question happened on X and Y and Z, you guys know that always X cross Y equals to Z, the direction. Even they are perpendicular to each other, always X cross Y and the final equation will become Z, right? 你们知道 X, Y, Z 的方向的定义吗？ You guys know? No? No? Okay. For the coordinate X, Y, Z coordinate, we call that rectangular coordinate. X, Y, Z, they are independent to each other. They are always independent to each other. They cannot affect others. They are, if I have only X component, I don't have Y and Z component. That meaning that these three directions, they are perpendicular to each other. Okay? So if you use your right hand, they will always obey the right hand rule. You use your right hand, you put the right hand in the X direction to Y direction. your thumb, the direction of your thumb is always the z direction. Okay? Okay. And one of the basics about the direction, the coordinate system. Okay, x, y, z. So for this one, because I cannot write this one, y means inside the y ball. Okay? Y means this direction, and s is this direction. X cross y equals to z. So z is the direction. Z is a normal direction, and s is the tangent direction. Okay, okay. Are you good here? I try to make our question to this one is easier to understand. I put x, y, z here. In our textbook, we use a more general way, but you should also think about what are them. Okay. So if our ET, meaning ET1 and ET2, if ET has only the component of x direction, all the ET is going to positive x direction. Okay, there's no y, no z. We can have your E. We can have your E in only x direction. For the equation here, we try to understand what is the direction, the relationship of E and the N and the H. We try to understand this one. Because our time is not changing, so we don't have anything here. Okay, we just don't consider this part. We left only curl E equal to minus M. Those are the relationship of direction of N and the E. Okay? And I try to write down an example if E is the direction of only to the X. Why? Because this is a condition, I try to integral the linear cross, a linear cross line here. So I have only E can obey this rule in these two directions. Okay? So only ET1 and ET2 has only X component. And we can write down that if the result E is EX, if you write down this one, EX, then you write down your curl E equals to, you just write down everything about a curl. I hope you still remember. That's why we need to learn curl in the first week, right? You write down x, y, z hat unit vector and differentiate to okay, you can come inside, it's okay. Yeah. You can divide it by x, y, z, and then you write down, because E has only x component, right? And for y and z, they are 0. Just write down that directly. Then you obtain the result. How? Just do the same thing. You do the calculation. You will find out that the EX can also have this part and have this part. Okay? Okay. And more, we will have the two directions, but which one can be cancelled? Which one? Which one can be cancelled?
Why?
Why? Why? What happened here? Let's think about that. EX is EX the same according to Z, or EX will be the same according to Y? EX will not changing according to Z, or EX will not changing across to Y. Think about it. Anyone? Will EX changing according to Z? EX here and here. Z is this direction. If the up and down, will that changing? Or will EX changing according to different Y? Y is inside and outside. Or maybe they will change, both of them can be left, right? Can anyone explain? Okay, try it. It's good. Yeah, it's good. But yeah, you will think about that before your midterm exam. Maybe I will try to have a question, but I will not use X, Y, Z. Maybe I put X, Y, Z in different direction. Yeah, then you should think that again, right? Why don't you think it now? This one will disappear. Why? EX will changing according to this one. Can you guys understand? Z is, you mean because it's on the boundary, so the result will not change according to Z, right? That's your answer, right? Anyone? So this one will disappear and then we left this part, right? Let's think about that. So S, Y, and the Z, and the minus Z. So you will left so your direction will be only down here. But we look at the textbook, you can see did you see that? What is the answer here? The answer is we have our M, the M is outside here. So you pick maybe a wrong answer, right? You understand? So your result will become, this is minus Y. So actually you left this one and you have a minus sign for that one, and this one is disappeared. In my opinion, you don't have component in the Z, but because we don't know how long the L is, we think all the we assume that TE2 and the the ET2 and the ET1, it is harmonic along all the line. So you might have only have this one. Y is inside， 不对，是你对。Yes, yes, Y 哈。那个 M 是出去。所以答案是对的。You are right, I think. Yeah, this is a single question. So this one is 0. Okay, you're correct. Yeah, this is yeah, I think he is the long Y X 对 Y 对 Y 是不会变，好像不对，对啊，应该是对，像我刚才讲的没有错啊，应该是它应该是会随之一变的，对，对不对？You assume the， 所以我刚才没讲错啊。I think I'm correct that the field is supposed to assume that it is uniform, because delta L is infinite. It's not 0. I try to assume this question. I try to explain this question along the line. So I need to assume at the beginning of this line is uniform, but we don't consider the line. I was assuming it's okay. I can still give you a card because you already answered 2. You try to answer 2 questions. Even the answer is not accurate, but I think it's okay. It's okay. You try hard, but the thing is. For this one, this is 0, right? Long Y 对，long Y 那其实是进去不会变，对不对？How to explain? How to explain? I need a reason to but actually maybe this is not the best way to explain a question. If you use your right hand to make a loop, maybe you can see the direction of n. But you use this one, maybe make you more trouble. I think if you use the hand for a loop, will be easier to find out. You cross the equation of E, then you obtain the direction. Okay, maybe this will not show up in the midterm. Okay, but you can think about that. If your direction of E here and the E here in the tangent direction here, you will obtain another boundary condition, that is ET2 minus ET1 equals to the direction of outside the paper, outside the whiteboard. The direction is perpendicular to the direction of the loop, okay? I don't know what is the direction of loop, but you use your hand to write down a loop, you will find out the... Yeah. Do you want this question in the midterm? Okay, right? Maybe just use your hand to put it down, then you will got the direction of them too. Yeah, I will think about that. I just think about that in this way, but I think I cannot explain very well. And the textbook didn't tell us the reason, just tell us the direction of this one will equals to ms is like close to x close to E2 close to n is outside. Yeah, got it. It's easy. Use your right hand. E2 minus E1, so the direction of E2 is going to this direction, right? Close to N, so that's why MS is outside. Okay, I think this is another explanation. But if you want to use the same way I explained here, maybe we need to think about that more, about why that's harmonic, why that's uniform, in which direction is uniform. But if you just use a pen, maybe easy, much simple for E. Okay, and because of E2 close N equals to MS. Okay, I think it is the definition of the curl. If it is a positive sign here, you put a curl. You put a curl edge here. You can put just unclose edge. So the direction of J is unclosed edge. If your definition of J is going to right, your edge is inside the paper. Okay? I think I find an easy way to explain that. X, S, Y, Z. If it is X crossed Y becomes Z. This means inside, okay? X, Y, Z. If I write it down. Close. A, because for any vector, the direction of this one will be N cross E. The direction of this one will the same. Okay. So, if I have a direction of A in this one, then N, if N means Z, if N means Z, if I write down this one, means I close to E and will be inside. Direction of Y. I make this notation. This is not a formal notation. This means the direction of curl A is in the same direction of Z cross E is the direction of Y. Can you understand? this is how I try to, this is only for X. Okay, this is how I explain this direction. If you put a curl, you use a normal direction close to your original direction and it becomes a new direction. Okay, take a rest. Yeah.
就是反正我试着去解释课本没有
As understood at first. So, finally we can obtain 4 general expression of the boundary conditions. Those are the result we obtain from previous 2 pages. So, in summary, I summarize the result that for this one is a dot, right? You use n. N is a direction perpendicular to your surface. Actually, it's the direction of your surface. You focus on only the direction of n. You dot n to d2 minus d1. Okay, we explain why d2 minus d1 because the direction of the surface, closed surface, in the top and in the bottom is different. Well, equals to rho s, and we explain what is rho s. It is q over delta s. Delta s is the area we try to explain here. So actually, this is like a unit area, right? So we will get. This is the charge density, rho s here. We can find the definition as well as here. Yeah, don't hesitate to read this, everything here. Actually, I try to explain well. So, rho s is surface charge density. This is the first one. And for another Gauss's law, for magnetic field equals to 0, but you have the same. But in our nature language, we try to explain in the physical meaning of these two, which means the normal direction of our D in the bottom in the bottom and top of these two medias, the difference between this direction, the D of these two directions equals to rho s. Okay, and for the B equals to 0. This is the normal direction of these two fields. You need to remember that D and the B, the definition of D and the B from here at the very beginning. Right, this is a relationship between B and the H and the relationship of D and the E. If you have different material, for example, this is air, you use B equals to mu 0 H. Remember, those are both vectors. You need to use this. But if this is something different, this material, we use only mu here, we will introduce these two in the second part of our chapter 1, okay? We will introduce more material we will describe more these two. But so far, what you need to do is try to remember D you look at the D, it looks like you are looking at the epsilon. The E is not, it's E field. But it's E times epsilon 0. Then you look at the B, is related to material, is mu 0 times H, okay? So D and the B, they have a relationship to material. And another two boundary conditions is you don't see B and D, you see E and H, right? And the direction of E and H equals to ms. This is, can you read that? Magnetic surface current density. I remind you that because you integral this one in the linear loop, right? So there will be a magnitude that delta L, you divide by your original M divided by your delta L, so become your new ms, and as well as JS. This is a much more formal way to write it down, because for the original Maxwell equation, this one is positive. Boundary condition. Because this one is equals to positive, right? So for this one, you don't need to change. The result is just uncross your original direction. The direction of this one is uncross to your edge. But for this one, you will see there's a negative side. So you will take the opposite direction to you will uncross your original direction. Okay? Okay, so after I make a conclusion, we can go through what happened. Let's see. So, if there is no charge, there's no charge, there's no source on the surface. I like it because I use 0, 0, 0 to this return, right? And I obtain that dn2 equals to dn1. You need to pay attention that there is an n2 and n1 because I put the n inside. I remain only the perpendicular direction, only the normal direction of n and d. So you obtain dn2 equals to dn1 in the, they are the same. If there is no source, these two are the same. Okay, and as well as bn2 equals to bn1. And there's a second relation, they are the same. Okay, and if there is no source, ms and the js, they are both 0, you obtain that E2 equals E1, but not just only E2. We say ET2 equal ET1, only the tangent direction. These two, the magnitude and also the direction of these two are the same. E. This is another D is E in this direction are the same, and as well as HT2 equals HT1. Okay, then you got those relationships because if there is no charge, current density, no charge and no surface current density, either electric or magnetic. Okay? Okay? It's a beautiful and a simple result we derive from Maxwell's equations. And there are more cases in your textbook. They talk about if there is a perfect conductor, we say that electric wall. What is the perfect conductor mean? Perfect conductor means your conductivity equals to infinite. It's a perfect conductor. However, in equations, what you need to do is put ms equals to 0. But you still, maybe you will have low s and js. But I think it's one of the special case, and also because the wait, yeah, I might say something wrong. Okay, so the definition of perfect conductor means there's no field in for the I say something wrong for the D1 for the material one, because it is a perfect conductor, so there is no field. Either H or E, they are both 0 because it's perfect conductor. And because it's 0, I put in that, so you can obtain that dn2 equals to rho s, and bn2 equals to 0, and et2 equals to 0 because this is fictitious. I think the reason is this is because 0 at the beginning, but actually I don't get it that it's not exist. You try to calculate in the end you say this is a fictitious and equals to 0. I don't know why. You can read the textbook and see what he said. Okay, but no matter what, it's easy. So no further, just equals to 0, and another direction. Okay. You remain these two terms. If this is a perfect conductor for the media 1, a better way to do it is make it 0. Okay. Yeah, you guys know if the material is perfect conductor, there's no field inside there, right? You don't get a signal inside the how to say that? 电梯怎么讲？
Elevator.
Elevator, electrical elevator, right? If you use your cell phone in an elevator, you cannot get a signal. It's like your material of your elevator. It is a perfect conductor, right? It's a good conductor. It's not perfect. Perfect is a zero. It's perfect conductor. So there is no electric field or magnetic field can be inside the perfect good conductors, but there are a little in good conductor, E or H. But in the perfect conductor, they just directly use 0. Okay, just put the 0. I think if you know the general form, just put something 0 and then you try to make it easy. So another case is if there is a magnetic world. I'm not very familiar with what is the magnetic world, but you can see that there will be a mirror theory, image mirror theory, something like in the last part of the chapter 1. I didn't use that a lot. I think perfect electric is more common to me, because for this one is the conductivity goes to infinite. But actually I'm not familiar with the magnetic world boundary. But in the textbook, he told us that for that case also everything equals to 0, but something different is ms exists, but rho s, because there is no electric source in that case. Okay. Yeah. I just show you these two because the textbook says so, but I will not use these two, the result of these 2 pages to ask you question, and you may not use these 2 later, but you will use this page to derive some result for waveguides for this one. Yeah. So for me, this page is more useful. For me, I will use that later, and actually, in the end of this chapter, we will use some. Because as I said, what happens if your wave is traveling pass through different material, right? You will need this. You will need these equations. So we will see them soon. Just make a mark, just mark it. We will see them soon. Okay, those are boundary conditions and we explain well. So, okay, this is the most important thing I'm trying to teach you, that what is the wave, what are the wave equations, what is E and H. When we talk about Maxwell equations, we say vector E and vector H. What are those? What do we have at the beginning? What do we have at the beginning? What do we know about E and H at the beginning? Anyone? What do we know about E and H at the beginning? Anyone want to try? What do we know? We need some clue to solve some equations to obtain the structure of E and H. But what do we know at our beginning? We have
both in the electric field.
Pardon me? You have both? Both. Do we have more difficult thing about E and H? Do we have something described? Maybe some equations they are talking about E and H, and they are always right. Do we? They want to answer?
Let me think.
Anyone? How about an E and H? What kind of a relationship we know at the beginning? We have Maxwell's equations. That's correct. Okay. Yeah, it's not a hard question, right? I'd like to give a bonus to. Okay, sure. Those are not hard questions. We are trying to explain the four Maxwell equations, right? Those are the hint. We can start to know about the relationship about E field and H field. Okay, so this is the origin about how we know about E and H. Maxwell's equation. You already did. You have some. So the answer, the first answer of your quiz is this four, right? They are the Maxwell equations in the differential form, phasor form, and the time harmonic, because you use the J omega here, and we will repeat using this again and again and again, right? For the boundary condition we did, right? We do the first time. Second time you use that again. We try to understand what are they from their relationship. Okay. Before we start, we try to make something disappear, to make it lay easier, okay? First thing, if there are no source, what happens if there are no source? I remember I mentioned that M, L, though they are source, okay? Source, you have charge, you have current, you have something there to make E and H field, right? If you don't have that, I use green, make that disappear. So 0, 0, 0. Yeah, good. Okay? So it's easier. This is the first thing. Second, I try to look at these two equations. Let's do it. First of all, I do the same thing as you. I write down Maxwell's equations. If you are a bad memory like me, I will try to help you to remember that, like you use a curl to E and the H first, right? And then you do different thing, but this is D because this is not only E but also consider your epsilon. Also, B equals. Okay, I will start from the bottom. This is 0 because I don't have the magnetic source, and this is Q, although, and I put that here, and I think it's the current density, right? So, low S, okay. And for these two, I know this is a negative, something negative, and this is a positive. This is the Ampere's law, and for this one, it's J omega. If this is the electric field, I put magnetic field B here minus this will be another source. It does not exist, and then something very similar to that in the pair. Okay, do I make anything wrong? Okay, maybe it's a notation, so it's just okay. The same. Okay, even that's a close, it's an open book test for midterm and final. Maybe you will try to. I think this is a way I remember them, okay, because you know they are very useful. Okay, all right. How about if we take another curl to the first equation? Yeah, I do the first one, right? Okay, what happens if I do that? Let's I do that. And because when we start, I told you that there is no source, right? So I can take this part to 0, and I take this part to 0, and I take this part to 0. Okay, follow me, and you will remember this very for all of your life. I hope so. I hope you can remember that. Okay, this is how we derive the equation, the wave equation. Okay, there is a minus sign, minus j omega. I will take minus j omega also. Okay, so I make it more beautiful. Become minus j omega. Those are the scalar I can take outside. I deal with only the vector part. Am I too slow? You think so? If I'm too slow, maybe you can tell me to speed up. Okay, the same thing. Okay, because B equals to mu h. Okay? No problem, right? Can you guys follow?
No.
No?
Epsilon. Epsilon.
Oh, did I?
Oh, okay.
No, it's correct. It's correct. Right? What is the curl h? Curl h equals to jd, right? Right? I'm slow enough. So J omega D. Okay? What is D? D is epsilon epsilon E. J times J. J means the square root of -1, right? So it's the I you know before. Okay. So J times J minus 1 times minus equals to 1 cancel out. Okay. We left omega mu epsilon E equals to omega squared times mu epsilon E. Any question? So if you have a double curl to your E field, the result will become omega squared times mu epsilon times your original E. Okay? Then we will introduce you another, this one, vector identity. If you take something for a double curl, write down this one. If something will equals to, I didn't remember that one. I just try to, this is just an identity 公式啦，公式而已。Okay, for that equals to gradient to the divergence A minus Laplace. Oh, guys, do you remember Laplace?
No.
We introduced Laplace in the first week, right? Now we use that now in the first week. This is Laplace, okay? Okay. Do you guys remember Laplace? What is Laplace? Laplace means, yeah, Laplace means, yeah, this one. I do that again. If I Laplace a scalar field, you will use this equation. If I Laplace something will equals to, you will scale Laplace to a plus x plus y plus z. This is just use the, I think this is the operator. 它只是一个像加减乘除的运算值而已。Laplace, okay? It's not big deal. And why is this one? This one is this one to x, y, z accumulate to each other. Okay, this is Laplace. I introduced in the first week, guys.
Yes.
Right? Yeah. That's why we need to take a video for a whole class. That's why I said you can look at the class. Then the video I already introduced that. I said that already. Okay, for Laplace. Okay. So, what can we do now? Look at this and look at that. similar. So this one can become, I'm talking about left part, okay? For this one, the right part is done. But for left part, I use the vector identity to transfer that to minus Laplace square E. Okay? Because of this identity. You can find this in the back of your book, appendix. This one always true. Okay. What else can we do? This one's still ugly. What is divergence E? I take a scale outside. This is epsilon E, right? And epsilon is a scalar, right? So we can still say this one is still true. 0, I like 0. I like 0. So finally, we obtain this term equals to that, which means Laplacian of the E field plus omega square times multiply mu epsilon E equals to 0. Similar thing happened if you use another curl to curl H. You will obtain Laplacian. Okay, you guys already remember this one? Try to delete them. H equal plus omega square mu epsilon H equals to 0. Okay? Still ugly? Right. I agree. Too many words. I don't like that. How to remember? I try to make it easier, so I define omega square mu epsilon equals to k square. Can we do that? Okay, we'll just define a new notation k equals to then. So k square. Okay, what we obtain? What do we obtain so far? We find from 4 Maxwell's equations. We use all of them, right? Already, and the vector identity, right? We just do another curl to first one and the second one, and we obtain that. This is an equation related only E field. This is the equation only related to H field, right? Your E field, if you take the Laplace, you take the Laplacian plus something, some square, multiply your E field equals to 0, it looks like solvable. You can solve here. You can solve E here. And you can solve only H here. I will tell you how to solve it. They are the second order of partial differential equations. You might see these two equations in your calculus class. You might. This is I think we call this one PDE. Have you ever heard this one before? PDE, partial differential equations. Those are the equations. You have special form for these two equations. Okay. We might K is the omega times the square root of mu epsilon. Omega is 2 pi f. Anyone remember where omega come from? Omega come from j omega, right? Why do we have j omega? Because if it is time harmonic, every field j omega can be derived and then go to j omega. This is where the j omega come from. Remember, right? It's time harmonic. You take a derivation respect to time, you get j omega. Is that omega? Where does mu and the epsilon come from? They are relationship between D and the E, relation between B and the H. Materials, frequencies. K is something in this form, okay? This is K. Okay, so result, they are wave equations. You use Fourier, you use Maxwell's equations to find what is E field and what is H field. That's what we do here. Okay? So wave equations. They are wave equations. If you cannot follow, still think I'm too fast, you can go to watch my video. Maybe you can look at the slide. The slide, I do that step by step, the same thing, but this is more beautiful. This is ugly because I write down. But this one is more beautiful, you can read. You take a curl, you change everything. See, for this part, you can follow the clue. I change here, and then because this is 0, so this one disappear. You get these two results, and those two are wave equations. What is the equation of the E field and the H field? And we define K squared equals to omega squared times mu epsilon. And K is important. K is important. K, what is K mean? What is K, what does K mean? Sorry. What does K mean? What does K mean? What is K? K have many names. Somebody call it propagation constant. Somebody call it phase constant. Somebody call it wave number. It depends on this situation. There are more deeper situation and more complex situation. Maybe we will introduce there. Maybe, but you can remember that at the beginning. It is sometimes K is beta. Well, I think you guys all, you heard beta before, right? When I say beta equals to 2 pi over lambda. For the class you took last semester, we talked about beta equals to 2 pi over lambda, right? Is K, if in some easy way, if the easiest case, what is the easier case for us now? We call it a TEM wave. It's a very easy wave. It's more, we will explain later, okay? Okay, so sometimes K is propagation constant, sometimes K is phase constant, sometimes we call this wave number. Oh, at this moment, you say, okay, there are 3 names of K. There are 3 names of K now, right now, okay? You just remember if you just start to understand that. Okay, so if our material is lossless, there is no loss. What does no loss mean? If your wave is propagating in this material, it will propagate forever. The energy will not disappear, will not decrease the energy. It will propagate always. Okay? So if the media is lossless, no loss, so that means mu and epsilon, those media are all real numbers. For the value, they are real numbers. You don't have the imaginary part. And K is real. Why? Because K equals to omega times the square root of mu epsilon, right? Real frequency is always real. So the three parts of them are all real numbers. You multiply them to each other. The K is always real if they are lossless. You guys got it? If the material is lossless, mu and the epsilon are real. If mu and epsilon are real, K is real. Okay. That means it's real happen. It means the number is real. There is no imaginary part. Okay. Which means that's easier to calculate for me. Okay. It's easy. You don't consider too much. Okay. So lossless wave equations. Beautiful and easy. Beautiful and easy. And the next step, after we obtain these two equations, what is the next step? The next step is to try to solve E and H. This is our goal so far, to solve E and H. And I will let how to solve E and H for next week because I think I don't have enough time to finish everything. So we will stop here and I will leave maybe 5 minutes to explain, or you want to ask a question to understand. This is important. This is important. I will start to ask Abi first, and if he don't have question, I will use maybe Chinese to. No, it's clear, right? Understand? Yeah. Okay, you know what we are doing here and why we are doing here, and then finally we got the equation.